Good afternoon. A warm welcome to the first National Space Day celebrations. It's delightful that India has recognized actually tomorrow, but a day in the year to celebrate space achievements of the country. It so happens that this also happens to be the year which started off with a wonderfully successful launch of POLX, Indian X-ray polarimeter, which was the primary payload on board ISRO's XPOSat mission. So I'm really proud to say that POLX was conceived, designed, and built at Raman Research Institute. And this has been happening for a long time. So I have, as I said, seen the last few years of it. But it's been very impressive that this decade-long sustained effort could go through. And that, to me, points to the uniqueness of Raman Research Institute. I've made this point so many times that I'm sure my colleagues are getting bored, but it's a fairly unique thing in RRI that scientists and engineers work together on frontier problems, and they are part of the same team, right? And I think that a wider recognition of that within the country in other institutions and centers would go a long way in us, taking forward frontier science. I mean, science and engineering have to happen together. Frontier science, happens due to frontier engineering, and then frontier science feeds back into new technology that technologists use. So I should formally congratulate my colleague, Professor Biswajit Paul, who led this project, and right from the start. So I have known of X-ray polarimeter, X-ray, maybe the names had changed, I don't know, but from the time I'm in astrophysics, so I knew that there was something cooking in RRI for at least a decade before I came or more. And he has really taken the project forward from fruition, to fruition, from just conceiving of it. And I congratulate him and all the members, present and past, of the POLX team. So a warm, greetings to you as POLX aboard XPOSat is taking data as we speak. I'm especially delighted to welcome our industry partners to Raman Research Institute for this event, and we deeply appreciate their contributions. Beyond the scientific discoveries expected from POLX, the current and future efforts at the Institute in X-ray group is towards hard X-ray optics, and we have Vikram Rana, who is working on it, and also with Biswajit involved. And I should also mention that we are partnering in another possible proposal that may turn into a space mission, which is called Daksha, and RRI is, the X-ray group is helping that happen. But broadly, as I said, this interplay between science and engineering at Raman Research Institute spans mind-boggling spatial scales. So our researchers work right from cosmology, cosmos, the largest scales conceivable in the universe, to the quantum domain. And we are leading in many domains of what has become very commonly known now as the quantum technology applications. So there's a national mission which has come up, and I expect that Raman Research Institute will play a significant role in taking that forward. And again, I really look forward to the partnership between science and technology, giving us an edge over any other place in the country. So the theme of this National Space Day is Touching Lives While Touching the Moon, India's Space Saga. I mean, very aptly, there's also a mission proposal from Raman Research Institute, led by two of our young astronomy colleagues called Pratush, which aims to send a high precision radio instrument, radiometer, to the far side of the moon. So it would orbit the moon, and the far side of the moon is protected from the radio frequency interference of Earth, and the time the spacecraft spends there can actually be enough over a couple of years to reveal a very, very precious signature of early universe, which is when galaxies formed. So it will have clear message from where and when and how galaxies formed in the universe. So we are pursuing frontier science and the partnership with engineering, and I think that is a story which will define Raman Research Institute in the decades to go. One of the stories, and I welcome you all again to this National Space Day celebrations at Raman Research Institute, and I request Vikram to take the proceedings further.
Hi, thank you so much, Tarun, for the motivational and kind words about the Polix. It gave a lot of boost to the Polix team for the next project. As you might have seen the program, we have a couple of items lined up for today. The first National Space Day. So in the next item, we have we are planning to release a couple of short videos. I think Tarun has already given some brief idea about the various projects that RRI will be involved in the space. So our science outreach team has made brief videos about a couple of projects that RRI will be participating, and this videos actually captures past, present, and future of RRI in space. So I would just request audience to just have a look at those videos.
Photons from cosmic X-ray sources can either have their electric field vectors randomly distributed, or it can be a net direction for some fraction of the photons. The latter is a case of polarized X-ray emission, and it holds important clues about the celestial sources, studies of which by other means like spectroscopy or imaging have been proven insufficient. Polarimetry is relatively an unexplored area in X-ray astronomy. For several years, the 8th Orbiting Solar Observatory, a 1976 NASA mission, was the only mission involved in polarimetry measurements. It had performed polarimetry measurements of Crab Nebula. Several decades later, yet another NASA mission, the Imaging X-ray Polarimetry Explorer, which works in the energy range of 2 to 8 kilo-electron volt, has revolutionized the polarimetry landscape. Speaking of the Indian contribution, the Indian X-ray polarimeter, also known as Polix, was designed and developed at the Raman Research Institute, Bangalore. Polix is an instrument on board the X-ray polarimeter satellite, which was launched by the Indian Space Research Organization on the 1st of January 2024. During its design lifetime of 5 years, Polix will measure the polarization of different types of astronomical sources. Measurements of polarization of X-rays emitted from these cosmic X-ray sources would greatly help astronomers to understand the distribution of magnetic field in these sources, the geometric anisotropies of these sources, and their alignment with respect to the line of sight. It would also help astronomers to understand the nature of the accelerator responsible for the emission of these cosmic X-ray sources. Complementing the IXPE, POLX will work in the energy band 8 to 30 kiloelectron volt. POLX instrument is based on an isotropic Thomson scattering of X-ray photons from a low atomic mass scatterer. Photons from the sources are made to undergo Thomson scattering, and the intensity distribution of the scattered photons, measured as a function of azimuthal angle, is related to the degree and the direction of linear polarization of the X-ray photons.
We need to take steps now to change the way we keep things secure. Classical security is not going to work anymore. We need a paradigm change, and that is what brings in quantum. Quantum security is a whole new way of keeping our data secure. The project we are discussing here today is called Quantum Experiments Using Satellite Technology. We need this security to be available to people across long distances. And so the problem Quest is trying to solve is this long distance problem. To have this quantum security extend over thousands of kilometers using a satellite as a trusted node. In the Quest project, we are attempting a first, whereby we are going to send what are called particles of light upwards. Well, we need to look upwards because the satellite is there, but what is different about this project is that our quantum resource remains on ground, and we send the particles up to the satellite, do what we need to do, and then two places are linked with each other using the quantum security. We have done the first in-lab free space quantum key distribution experiment, and this also had competitive rates and better rates than the previous ones from a group in NASA. Later, we followed this up with a first in the country where we actually showed a quantum link between two buildings at Raman Research Institute using the atmosphere as a free space link. The third important thing we did was actually move our receiver. Now this is very crucial because a satellite does not remain stationary on top of you in the low Earth orbit. It is going to move, and so you need to keep looking at it, pointing at it, acquiring data from it, and tracking it. And this is a very hard problem to combine with the precision required in quantum communications. And we have been able to show this terrestrially by using a moving receiver platform. And so we are now poised with the absolute know-how of what it is we need to fly in the satellite as a payload. Currently, we are working on the first version of the quantum payload, which is going to fly in a satellite, and hoping that we get the right resources and the support from our collaborator agency, which is Indian Space Research Organization, as well as the Department of Science and Technology and other agencies in the National Quantum Mission, so that we are able to do this in a competitive time frame. What I can definitely end by saying is that we have a fantastic group here at RRI, not only my lab members, but also the electronics engineering group, the workshop, the computing department. All of them have come together to help us achieve this first, and I'm sure they will continue doing that, provided we get the right support from the external agencies as well. We are ready for a first.
Pratyush is a space-based radiometer, and the science goal of Pratyush is to measure the faint signals coming from the first stars and galaxies in the universe. And this is often regarded as one of the final frontiers of cosmology in trying to understand what these first sources were and how different they were compared to the current universe we see around us.
So Pratyush is a radio experiment. It's going to operate between 55 megahertz to 110 megahertz. And it's looking for a signal that's coming to us from all directions in the sky, so not at a specific direction. The ideal place to do an experiment to detect the signal from the first stars is to go to a place that is radio quiet, without any atmosphere or ionosphere, and in free space. And one environment that is accessible to humankind is the far side of the moon. So Pratyush will orbit the moon. It will take the data when it is on the far side of the moon, the side you don't see, and it will transmit data back to us when it is on the near side.
Given the faintness of the signal, a very small miscalibration in an instrument can really give you very high systematic levels compared to the signal. So based on our experience designing ground-based experiments with exactly the same science code, we proposed Pratush in 2018 to ISRO.
We have a memorandum of understanding with the Space Application Center Ahmedabad, which is a wing of ISRO. And we have submitted a joint proposal for phase 1 of Pratush, which will do this initially in Earth's orbit before eventually going phase 2 to the lunar orbit. On the basis of this proposal, we got some seed funding, and using which we have come up with a baseline design of Pratush. So what you see on top is the antenna, but integral to the antenna design is also everything that the antenna sits on. So what you're seeing below, this cuboid box-like structure will house both the electronics for the experiment as well as the spacecraft electronics, which will do communications, power management, etc. So in our lab, we have built the full model, lab model of the antenna, as well as all the receiver electronics, and we have been reaching close to the sensitivity levels we need to do the signal detection.
So our final idea is, given the extreme precision required to design such experiments, we need to operate in more pristine environments like space. And idea is that we'll have ground-based observations, space-based observations, and basically if we see anything, and if we see the same thing in both experiments, it will be added significance to the claim or the results that we will present.
In a fresh impetus to X-ray astronomy, Raman Research Institute, along with the Indian Space Research Organization and the Physical Research Laboratory, is gearing up to possibly building yet another payload for a future X-ray space mission. Soft X-ray Telescope is a payload on board the Indian astronomy mission AstroSat, launched in September 2015. It has the capability to focus X-rays up to about 10 kV. In the newly proposed Technology Development Project, scientists aim to build an instrument capable to reflect and focus hard X-rays and hence study celestial bodies in the X-ray band higher than 10 kV. Presently, the 2012 launched Nuclear Spectroscopic Telescope Array by NASA is the only space mission that focuses hard X-rays. Scientifically, it is very important to have accurate measurements of hard X-rays as they are produced via non-thermal processes occurring in the universe. Measuring hard X-rays can help scientists study details about the synchrotron emissions, some nuclear processes, inverse Compton scattering, and more. The toughest technical challenge, though, lies in focusing the parallel beams of X-rays onto a small desired spot after being reflected from two curved surfaces, in this case, a parabola and a hyperbola. This requires the X-ray photons to incident at a very small angle, which is typically less than a degree. To gather the maximum X-ray photons, a large collection area is achieved by placing mirrors one inside the other, resembling onion peels. The mirrors are coated with a combination of materials like tungsten silicon or platinum carbon to enhance reflectivity at higher energies. This precise arrangement of hundreds and sometimes thousands of curved mirrors in a coaxial and confocal manner determines the optimal performance of any X-ray telescope. The X-ray astronomy team at RRI is on a path to develop novel techniques for this mirror assembly design required for future hard X-ray missions. X-ray optics is therefore vital to be able to achieve two-dimensional spatial resolution, reduction of background photons, and thereby achieve high sensitivity, ultimately to obtain clear and sharp images of celestial X-ray sources.
Okay, I hope you enjoyed the video, you liked it. This, as I mentioned, gives you the glimpse about the possible future projects that RRI will be involved as far as the space is concerned. Now it's a time for our first lecture for today's, of course, first National Science Day lecture. And I request our director, Tarun, to introduce today's speaker.
Okay, so to commemorate National Space Day, RRI is happy to introduce another annual feature in its program of talks, and we would be having a National Space Day lecture. And one couldn't have asked for a better occasion. As I said, we seem to have picked up the year of POLIX, and I'm really delighted that we have picked up also the POLIX man to deliver the National Space Day lecture. So Professor Biswajit Paul will deliver the inaugural lecture in this series at Raman Research Institute. So Professor Paul received his master's degree from Vishwabharati University, Shantiniketan, and a PhD from Tata Institute for Fundamental Research. After stints in ISAS, Japan, and TFR, he joined as a faculty at the Raman Research Institute in 2006. So he contributed to the development of pointed proportional counters of the Indian X-ray astronomy experiment flown on IRS-P3 and the large area X-ray proportional counter, LAX-PC, of AstroSat. As PI, as I mentioned before, Biswajit led the team that conceived, designed, and built POLIX, the primary payload aboard the ExpoSat mission of ISRO that was launched on 1st January this year. His research interests are around the high magnetic neutron stars in the binary systems that emit X-ray pulses by process of accretion. Broadly, he has deep interest in many aspects of X-ray science and largely focused on compact objects, but even broader than that. So he is the country's leading X-ray astronomer, and also one of the rare things in India is can build instruments. So he is possibly amongst the very few people in India who has the capability to build X-ray astronomical instruments. And I'm really delighted to open this series of National Space Day lectures with a talk by my colleague, Professor Biswajit Paul. Biswajit.
Thank you, Tarun, for the invitation, and it's nice to see the hall full. This gives me an opportunity to look back. So when Tarun invited me, I was thinking about what to talk about. While we are delighted to have built POLIX, which is now in space, so I would end my talk with where POLIX is right now. But I thought this is a nice opportunity for me to look back. Over about 30 years that I have worked in X astronomy, and another about 30 years since X astronomy started in India. X astronomy as a subject started early 1960s when X-rays from SCO X1, a very bright X-ray source in the sky, was discovered, somewhat accidentally. India got into X astronomy from almost very beginning with balloon-borne payloads and rocket-borne payloads from Tata Institute of Fundamental Research in Bombay and from PRL, Physical Research Laboratory in Ahmedabad, initially doing rocket and balloon experiments, and over the years slowly moved on to satellite based experiments. So I would like to take you through the history of X-ray astronomy in India. I shouldn't say X-ray astronomy in India because astronomy nowadays is an activity which is done, for which data from all major international observatories are open. And in India today we have more than a couple of hundred X-ray astronomers practicing X-ray astronomers in, other than the educational institutes, other than the research institutes in major educational institutes as well. So people use data from almost all available X-ray observatories while pursuing their favorite topic. So I would be restricting myself to science that has been done primarily with instruments built in India, and that's the main topic. So very briefly take you through why X-ray astronomy. Astronomy people have been doing for centuries. It's last about 60 years that we are doing X-ray astronomy, and X-ray astronomy allows us to study certain things for which traditional optical astronomy or radio astronomy or certain kind of radio astronomy is not ideally suitable. That's this. X-ray astronomy allows us probes of extreme conditions in the universe. That's the key. Extreme conditions in the universe. That's extremely strong gravity, like when something is falling onto a black hole or very close to a neutron star. Extremely high density. In case of black holes, you wouldn't even talk about density. But in case of neutron stars, they have density which is like an order of magnitude higher than density of nuclei of atoms. X-ray astronomy allows us to probe temperatures which could be tens of millions degrees. It allows us to study magnetic field, properties of matter in magnetic field ranging between 10 to the power 8 Gauss to as much as 10 to the power 15 Gauss, way beyond anything that can ever be conceived for a laboratory experiment. Along with high density, it also allows us to probe certain low density regions in the universe which is not accessible otherwise. For example, if you take a cluster of galaxy, the matter in between the galaxies can be extremely thin. Okay? Even that can emit copious amount of X-rays, and X-rays are the best ways of investigating intergalactic medium. Where particles get accelerated to relativistic, super relativistic, very highly relativistic velocities, their interaction with other particles or their interaction with magnetic field produces X-rays. So these are various extreme conditions in the universe for which X-rays are very well suited. Okay, certain aspects can be seen in gamma rays as well, certain aspects can be seen in radio as well, for example, study of jets. But X-rays allow you to probe most of these things with, in the X-rays are the best possible ways. So what are the kind of objects which emit X-rays? Isolated neutron star, isolated white dwarf, etc. can be X-ray emitter. It's even better when you have a compact object, either a neutron star, a white dwarf, or a black hole, in a binary system. Okay, if the compact object is given a chance to draw out some material from a companion star, the material falling onto it can convert its gravitational potential energy to electromagnetic radiation, and that will primarily be in X-rays. Supernova remnants, after a star explodes, the outflowing material interacts with the interstellar material, gets heated up, and they are good X-ray emitters. There are also sites for acceleration of particles which can then eventually emit X-rays. So particles accelerated in supernova remnants, pulsar wind nebula, the jets which come out from black holes, they are all sites for X-ray emission. Hot gas, primarily seen in clusters of galaxies, as I said, is a very good X-ray emitter. Accreting supermassive black holes. So if you have, like at the center of our galaxy, we have a 4 million mass black holes. There are some galaxies with much heavier supermassive black holes. Anything falling onto that can produce conditions which can produce X-rays, and therefore X-rays are a good way of investigating them. There are objects called magnetas, where you have magnetic field strength in the range of 10 to the power 14 Gauss to 10 to the power 15 Gauss, and they can emit X-rays, sometimes as a continuous emission, sometimes in bursts. There are gamma ray bursts, which are phenomena that happen randomly and isotropically anywhere in the sky, can happen any time. Gamma ray bursts are also known to be associated with gravitational wave events. There is one evidence of seeing gamma ray bursts simultaneously with the gravitational wave when two neutron stars collapsed. Coronal stars can also emit X-rays. Sun itself emits copious amount of X-rays, but sun-like star is usually not of interest because their X-ray to optical ratio is extremely small. So there are many kinds of objects, many objects in the sky where you can study interesting physics if you look at them in X-rays. And the X-ray emission processes could be black body if the objects are very hot, could be bremsstrahlung if there are accelerated electrons. If there is magnetic field as well, then you can have synchrotron emission. If accelerated electrons find low energy photons to interact with, they can cause inverse Compton scattering. The low energy photon can then show up in X-ray band. You can have line emission from material. In X-ray astronomy, for example, lines from iron, lines from silicon, carbon, oxygen, neon, etc. are quite prevalent. You can have fluorescence emission, you can have radiative recombination. You can also have nuclear emission under suitable conditions, for example, in supernova explosions. And sometimes instead of emission, you can have absorption, cyclotron resonance absorption feature, which is seen in neutron stars with very high magnetic field. So there are many reasons, many objects, many astrophysical processes which can produce X-rays. Coming to X-ray detectors, now it's time to talk about detectors. Okay, if you want to detect X-rays, what all you need to do? You may want to do imaging if you are looking into structures. You may want to do spectroscopy if you want to understand the processes, if you want to study the abundances, ionization state, temperature, etc. If you are interested in variability, then you would, like pulsations, then you do photometry, just count number of photons. And some of us are interested in polarimetry. Quite often, you do more than one of these with a given instrument. Okay, you may do imaging and spectroscopy together, or spectroscopy and photometry together, and so on. Detectors available for us are scintillator detectors, which work in higher energy band, relatively easy to make. Gas detectors, slightly harder, but I would say easy to make. There are proportional counters, Geiger-Müller counters, etc. You can have certain kind of semiconductors as detectors. A special type of semiconductor detector are the X-ray CCDs. X-ray CCDs are quite different from optical CCDs. You can attach a grating at the with your X-ray telescope, and most advanced of all spectroscopic devices are these calorimeters. Okay, calorimeters is one where you use a transition edge sensor, and absorption of an X-ray photon causes slight increase in temperature of an object kept at its transition edge, and that can be measured very accurately. The energy can be measured very accurately. That's called calorimeter. X-ray astronomy is one area where even a simple detector, just like a photon bucket, can be extremely useful. Instead of a telescope, sometimes just having a photon bucket, like a detector with a mechanical collimator attached in front of it, so that you look at one object at a time, or one bright object at a time, can be extremely handy. So a lot of science in X-ray astronomy has been done with just these photon buckets called non-imaging instruments. If you want a telescope, X-ray telescopes are hard to make, as the video showed you earlier. You require X-rays to be reflected from a gauging incidence surface. If you want to go to higher energy, then that surface has to be graded multi-layer optics. Difficult to assemble. So X-ray telescopes are very difficult objects to make. Some amount of or certain kind of imaging is possible even without a telescope, with a technique called coded aperture mask. If you have a position sensitive detector and you put a mask of a certain pattern with a certain pattern over it, then an X-ray object will form a shadow. Okay, and looking at the shadow pattern, you will know where the object is. Even if there are multiple objects, you can make a measurement, deconvolve it, and you will get you will be able to identify the bright objects in the sky and measure their intensity and spectrum as well. A special technique is Compton telescope, where you have a high energy gamma ray. But this is probably, in all of astronomy, this is probably the most difficult for making X-ray images. Photons above an MeV or so primarily interact via Compton scattering. So if you have a device where X-ray photon has gone through a Compton scattering, and after scattering it got absorbed somewhere else, by measuring the energy at both of these, okay, you can find out a cone from which the photon must have come. So one photon does not tell you which direction it has come from, but if you have many such cones, the overlapping regions will tell you where the sources are. So that is Compton telescope. And polarimetry is done by the technique of Bragg reflection or photoelectron. When an X-ray is absorbed in a gas, the photoelectron would tend to go along the electric field vector, or by scattering. So the polarimeter that we have worked on uses this principle of scattering. X-ray astronomy is also one area where you can just send an open detector. Even that is very useful. For example, if you want to detect gamma ray burst from the sky, you would send an omnidirectional open detector. And in X-ray astronomy, we also have something called all-sky monitors. So there is a vast range of technologies available. You have to choose the one that serves your purpose. No matter what you choose, you have to send it to space because X-rays get absorbed in the atmosphere. So in the X-ray energy band, you necessarily have to take your instrument above the atmosphere, either with a rocket or with a balloon or with a satellite. Satellites are of course expensive and hard to come by. So in between satellites, one does rocket experiment and balloon experiment, where you have, with a rocket you can get up to few minutes or 10 minutes kind of exposure. With the balloon you can get few hours of observation, and with the satellite you can go on observing. List of major X-ray observatories is given here. This is about half of all the observatories which have been flown. In my mind, the most important one was Uhuru, which was the first satellite ever sent into space to do, and it did a survey of the sky, found out all the bright ones, which are then subsequently studied in detail. So Uhuru was the pioneer. Chandra X-ray telescope of NASA, this is the one which has highest angular resolution, 0.3 arcsecond. XMM Newton is a European mission which had a few arcsecond angular resolution but very large area. In my mind, these three are the major, most impact-making X-ray mission. Someone else will have a slightly different take perhaps. The three instruments which have been sent from India are IXAE. This was an experiment sent in 1996 on IRS-P3 satellite, AstroSat launched in 2015, and ExpoSat launched earlier this year. These are the satellites which are launched in 70s, 80s, 90s, at the turn of the century, first decade of this century, second decade, and satellites launched in the current decade. Many of them are functional in space. So over the years 1970 to 2024, these are the satellites which are the major satellites which are launched into space. All of them are dedicated X-ray instruments. What happened in India? Let me quickly take you through what happened in India. As I said, India got into X-ray astronomy from very beginning, okay, in early 60s. The Physical Research Laboratory at that time started rocket experiments, and sources like SCO-X1 and few other, the most bright sources were observed. The things at that time, these were the very early days of X-ray astronomy. If you could measure the intensity of a source, you could say something. If you had 4 beams to measure a crude spectrum, you could say something. If you could measure variability of a source, I mean, if you could measure a source for a few minutes, and if you saw intensity variation within that, you could say something important about the sources, because these are very early days. Even knowing that source intensity varies in a short time scale allowed you to say that the source is compact. Okay, so early days you had to make simple measurements, and India was very competitive at that time. During 60s, 70s, up to early 80s, rocket experiments from PRL, multiple observations of bright sources. Balloon experiments from TIFR, again multiple measurements of bright X-ray sources. As I said, like, if you just measure intensity variation, if you could measure intensity variation, it had an impact, okay, those days. Few measurements at different energies combined with everything else available at that time allowed you to say that, for example, the spectrum of a source was not only thermal, it also had a non-thermal component. Okay, so if the objects are powered by accretion, it's not only emission from the accretion disk, which would be of thermal nature, therefore have lower energy. You could also say that these objects have corona, okay, which is required to cause inverse Compton scattering and thereby produce higher energy X-ray photons. So this kind of experiments went on. The first opportunity for satellite came with the first satellite that was launched from India. Both PRL and TFR group were quite active in the 70s and 80s. The first satellite also had an opportunity to send a X-ray instrument into space, and a very small proportional counter was sent, 15 square centimeter. The satellite Aryabhatta actually made into Indian currency and Russian postal stamp. Unfortunately, the instrument did not work very long, but whatever few days of observation was possible, one could measure the spectrum of sources like Cygnus X1, another low-mass X-ray binary, GX17 plus 2, and comparing measurements with Aryabhatta with the any measurement done before, one could say that these objects not only vary in intensity, even their spectral shape changes with time. Next was Bhaskara 1, on which an all-sky monitor was flown. I think the prototype was made in TIFR and the final instrument was made in PRL or SAC. Unfortunately, this instrument, no further details are available. I think the instrument did not work long. Both the satellites lasted long, but the instruments did not last long. These were early days, and one was still figuring out how to make things work longer in space. All the quality assurances, etc., were based on the initial experiences. While ISRO was preparing for more reliable launcher, bigger satellites, and so on, TIFR concentrated more on what was possible with the technique available at that time. TIFR took up some rocket experiments, however, with very low energy detectors. For example, detectors with extremely thin window, which allows you to measure X-rays at a low energy. Okay, the moment you have measurement at low energy, this is for example from a cluster of galaxy, you could see that the power law emission does not continue. At lower energy there is a turnover, and this turnover is because of absorption. Okay, so you had a way of measuring the absorption along the line of sight towards the cluster and so on. With a better and bigger similar detector, X-ray detector with sensitivity to very low energies, it was possible to take up survey and mapping of extended regions. Okay, these are one of the first all sky map or maps of very large area of the sky in the soft X-ray band. These happened to be just before the German satellite ROSAT, which was launched I think 84, lasted for 3 or 4 years. Subsequently, ROSAT gave much better and higher quality images of the entire sky. But pioneering measurements of this kind of things were done from India in the early 70s and 80s with whatever resources that was available with us. When efforts were going on in ISRO for bigger and better launcher, more reliable rockets, satellites, and so on, TIFR group on the other hand was concentrating more on detectors, okay, to be in a position to make reliable detectors which will last in space for long. Effort was led primarily by Professor P.C. Agrawal. This instrument, two xenon field proportional counters with a large effective area, large geometric area, was built during late 70s to 90s, and I happened to join the TIFR group early 90s, and few years before me, Barsha Chitnis had joined. So these are observations with this instrument which was flown on balloon. These are two proportional counter detectors on a structure weighing about 450 kg, would be sent on balloons. Okay, it would go up to 42 kilometers or so, where the residual atmosphere is very low, only about 2 grams, 2.5 grams, so that you can study X-ray objects. We could typically get few hours of observation duration. Now you can see these are spectrum measured of Cygnus X1 with this instrument. Early compared to earlier where you had 3 or 4 spectral bins, now you have 20 odd spectral bins. Okay, and combining this data with low energy measurements available elsewhere and very high energy measurement available from a NASA satellite mission, one could study the X-ray spectrum, very broadband X-ray spectrum of black hole sources. Okay, and that told us a lot about the acceleration mechanism, the fact that these sources need to have 2 emission components, one from the disk, one from a corona surrounding it. I took up a study of accretion pulsars with the same instrument. These are the pulse profiles of my favorite source, GX1 plus 4, on 2 different occasions. Now, from a neutron star, if you see 2 different pulse profiles, what can change in the beaming pattern of the neutron star? Not orientation of the neutron star, or not the angle between the magnetic field and the spin axis. So keeping those numbers as constant, orientation of the neutron star and angle of the neutron star with respect to our line of sight and magnetic field and neutron spin axis, keeping those numbers which have to be fixed, keeping those numbers fixed, we modeled the pulse profiles assuming equatorial X-ray beam and a polar X-ray beam, and we could determine the angle between the spin axis and magnetic axis of this pulsar. Now, since then, these kind of modelings have become far more complex and involved, but the basic principles remain same. People have now introduced GR effects and so on, the gravitational bending of light as it comes out from the neutron star and so on. This instrument, I would say, was the basis for all the subsequent satellite experiments that India got into. Okay, this was evidence that sturdy, long duration instrument can be made in India. Entire electronics for that can be made in India, not only the detectors. The TIFA group led by Professor Agrawal met that basis, and this experiment, as I said, went on from 70s, 80s, mid-90s. In mid-90s, we had an opportunity to launch, make and launch a set of instruments for an Indian satellite. The first polar satellite launch vehicle unfortunately was not successful. It was figured out why it failed. Second one was successful. So for the third one, there was a call, and we got an opportunity to make an instrument for the satellite, which would be launched with the third PSLV rocket. The satellite name was IRS-P3, Indian Remote Sensing Satellite P3. It had several remote sensing instruments, but we got a little deck space. These 3-pointed proportional counters, very simple detectors, X-ray proportional counters with a collimator on top. Okay. The challenge was you have to make it work in space. The high voltage supply has to be stable, it should be controllable, and the signal that comes out has to be processed properly and sent down, and as any space instrument requires, you have no control over it once it goes out of your hand. This was particularly important because the experiments on Aryabhatta and Bhaskara did not last very long. Fortunately, the instruments IRS-P3, which was a collaboration between TIFR and the ISRO group, led by Dr. Marar and Dr. Sita at that time. This instrument on IRS-P3 was launched in 1996. It lasted for 5 years in space without any significant degradation of the instrument. But we were a little unfortunate that this instrument happened to go on a satellite which was a polar satellite. So it would go from north to south, okay, because there are remote sensing instruments which require a polar satellite. It would go north to south. That means it would go past this very high density of charge particle regions with very high density of charge particles. These are the mirror points where charge particles trapped in Earth's magnetosphere bounce back and forth. So, there is very high density of particles there and the South Atlantic anomaly region. So, as the satellite goes north and south, we would get to observe only for about 15 minutes every orbit, few orbits a day. Plus, since the time was shared with other remote sensing instruments, X-ray observation was allotted only when the weather is bad and you can't really do remote sensing observation, okay, unless there was a very interesting science case. Nevertheless, if you have an instrument in space, you end up getting a lot of data. So we use this instrument few months a year for continuously for 5.5 years. And a few of the science topics I would like to spend a few minutes on, because this was IRS-P3, success of IRS-P3 instrument was the basis for AstroSat, all said and done. We observed accretion powered X-ray pulsars, we detected quasi-periodic oscillations in accretion powered X-ray pulsars. Quasi-periodic oscillation happens when matter falling onto a compact object, it's in a disk. If there are inhomogeneities in the disk, this inhomogeneity happens over a range of radius, okay, and as this material goes down onto the compact object, it produces quasi-periodic oscillations. So oscillations which are not quite fixed in frequency. So they end up giving you a slightly broad signal. I'll talk a little more about that. One result from pulsar observations with this instrument actually had a long-lasting impact on me. One transient pulsar was observed with this satellite, and if you see the period evolution of this source, there is as the matter is accreting onto the neutron star, it's getting spun up, so the period decreases with time. But you can see at certain epochs the period is significantly different from a continuous decay. Okay, sometimes it is larger, sometimes it is smaller. And if you compare that with the binary phase, you could say that what we are seeing is Doppler effect. As the neutron star is coming towards you, the pulse period seems smaller. As it is going away, the pulse period seems larger. Another way of looking at it is, instead of the pulse frequency, you can see the pulse arrival time. Okay. This is what got me into this topic of studying orbits of binary systems by looking at the pulse arrival times of neutron stars. Okay. And if you do it carefully, or for one full orbit or a significant fraction of orbit, you can measure the orbital parameters. And if you are patient, if you have enough patience, you can do it for a decade, you can do it for several decades. Okay. And measuring these orbital parameters again and again and again and again allows you to measure evolution of binary orbits. Okay. Why would one care about evolution of binary orbits? One obvious reason is that some of these, I dropped nothing, no. Some of these binaries have a neutron star and a massive companion. The massive companion is eventually going to go through a supernova explosion and leave behind another neutron star or a black hole. Okay. So these are progenitors of double compact binaries which will eventually produce gravitational waves. That was one. Another interest is, I am studying an object and how rapidly it evolves. Is a natural thing to ask for. These objects happen to evolve with a time scale of 100,000 years or so. And this actually led me to all subsequent studies of orbital evolution of these X-ray binaries. Another class of objects that we studied with IRSP3 was black hole binaries. Launch of IRSP3 also kind of coincided with appearance of a very interesting object in the sky called GRS. This is the name of a satellite which discovered the object. 1915 plus 105, that is just the coordinate of this object. Good thing about this object is it's a black hole accreting material from a companion star. It produces very powerful jets. Okay, the jets can have speed very close to speed of light, maybe 97%, 98% of speed of light, and the jets happen to coincide almost with our line of sight. Okay, then what you see is purely a geometric effect. The components which have been, the jets which are thrown out from the companion star, from the black hole starts moving out, their velocity in the sky will appear to be superluminal. That's why they are called superluminal motion and these objects are called microquasars. Forget that part. This object, because of the superluminal motion, became everybody's favorite. A lot of people jumped in to study this, and we were looking at this in X-rays. What we found was this object showed very rapid intensity variation, and rapid intensity variation with earlier generations of instruments, you could measure minutes or hours time scale variation. With this instrument, we could measure sub-second variation. Okay, about 100 millisecond time scale, we could see that the intensity varied by more than factor of 2. That clearly tells us the object size has to be smaller than the variability time scale, the light travel time across for that duration. So obviously, it points towards a black hole. We detected quasi-periodic oscillations. I'll come back to this little later. What was completely unprecedented was we saw in the X-ray intensity profiles of these sources. These are like 500 seconds X-ray intensity profile shown for different days. You can see very interesting patterns. Intensity goes up, comes down, goes up, comes down. Some days the variability changes. Some days it is very wild. This object later on was investigated in much more detail with the RXT satellite, because RXT which was nearly simultaneous. RXT did not have this limitation of 15 minutes in a day. RXT also had the spectroscopy along with timing. It had more advantages, but first time observation of this kind of pattern from a source in sky drove us crazy. Okay, we came to a conclusion that at least these patterns, which are later called heartbeat pattern in black hole sources, and I think there is one more source in which this has been observed subsequently. How we interpreted this was Professor Sandeep Chakrabarty, who was a theorist working on black hole accretion disk, had already proposed, without seeing any of our light curves, that this accretion onto black hole can have shocks. Okay, and when you have shocks, there will be wave generated, and material falling onto the black hole will not fall uniformly. Instead, there will be waves of material falling in. Okay, this then looked very much like what you would expect if a lump of material is falling onto the black hole. As it goes closer, temperature increases. We had light curve in two intensity band, two energy bands. So you could take the ratio and determine actually the temperature is increasing. Okay, temperature increases, then it suddenly falls. What produces that kink, we don't know, but it was seen very regularly. So this we had interpreted in a little bit of a hurry, but I'm very happy to see and know that it's almost 3 decades since then this has still survived. This is taken as a possible evidence of black hole event horizon, matter going and disappearing into the event horizon of a black hole. Of course, this was very thrilling. What I found personally even more exciting from the same source, analyzing its light curves those days, IRSP3, that particular instrument, I had worked on all aspects of it, and the last bit of software also was written. When I was analyzing the light curves of this black hole source, on light curves of some days, we saw, if you see the power density spectrum, there are these features. This feature would be extremely sharp if it was a pulsar. Okay. Some sources you see it to be broad, and that's called quasi-periodic oscillation. And quasi-periodic oscillation is now such a common thing in X-ray astronomy. Okay, you attend an X-ray astronomers meeting, every third sentence will have the term QPO. Okay, but it was not so then. In 1996, this was the third black hole object in which quasi-periodic oscillation was discovered, was seen. So you can imagine my excitement detecting this with our own instrument working in space, 1997, I think. This perhaps was the single most exciting moments in my astronomy career. IRSP3, even though it was a simple photometer, just measuring count rate into energy bands, okay, gave us pretty good data sets on large number of pulsars and black hole X-ray binaries. And I think that's where ISRO got the confidence that instruments which will last long and which will have impact can be made in India. And there are detailed accounts of how AstroSat was conceived and eventually built and so on. You can read articles if you are interested. AstroSat is a collection of 5 different instruments: a soft X-ray telescope, a large area xenon proportional counter. This is an even bigger version of what was flown on balloon. A new invention, a cadmium zinc telluride imager, where you have it's a Corrida aperture points instrument. I'll tell you a little bit about it. Then one scanning sky monitor. This is all sky monitor kind of instrument, and then there is an ultraviolet imaging telescope. So out of these 5 instruments, the large area X-ray proportional counter and ultraviolet imaging telescopes are kind of the workhorse or biggest instruments of AstroSat. Remaining ones kind of play a supporting role. The X-ray optics I will not get into detail except to say that it's very difficult to make, and this was not the technique used. You need this kind of a shape, multiple buckets, put one inside the other. That becomes upcoming project is all about. In case of soft X-ray telescope, this was made in quadrants. You make quadrants of it and a very large number of them, and then place them in a concentric manner. The large area X-ray proportional counter is basically what was flown on balloon, but bigger and made better and made to last long. 3 of those were made for AstroSat. The cadmium zinc telluride imager is a set of position sensitive detectors, about 1000 square centimeter area. Position sensitive detector works in the high energy band with a coded pattern of mask on top. So this is what allows you to do X-ray images in the hard X-rays, okay, because otherwise hard X-ray imaging is very difficult. So these are the main X-ray instruments on AstroSat which led to quite a lot of scientific studies. There is absolutely no time to get into details of what science studies have been done with AstroSat. I just listed here the section heads of a review article that Dr. Sita and Dr. Kasturi Rangan wrote a couple of years ago. Okay, so not going into details of science which has been done with AstroSat, you can at least see the in a list of topics which have been pursued with the X-ray instruments on AstroSat. And about 250 articles have been written, and the UV telescope has its own additional science. Nevertheless, I will take 2-3 minutes to very quickly take you through some of the science that me and my group have done with AstroSat very, very quickly. We detected thermonuclear X-ray bursts in rapid succession from one of the thermonuclear burst sources. Thermonuclear burst is when you have on a neutron star matter falling, which gives rise to X-rays. But this infalling material is a collection of hydrogen helium, okay, or pure helium, and this is a fuel. Okay, under extremely high pressure, sometimes that fuel can start burning, and it can burn in one lot, which is called the thermonuclear explosion. The X-ray intensity will go up by a factor of 10 or so, and then in few seconds it will settle back. Okay, we found typically these things happen at hours or several hours interval. Okay, we found a case where 3 such thermonuclear bursts happened in rapid succession. The AstroSat large area X-ray proportional counter has effective area in hard X-rays which is several times larger than anything flown before. So naturally there are interest in doing science in the hard X-rays. We detected, for example, cyclotron line in multiple sources. One cyclotron line shown here, another in a different object, a third in another object. We detected quasi-periodic oscillations in going to hard X-rays with lax space instrument. We detected quasi-periodic oscillation in yet another objects. We measured orbital evolution. I said, we can do the pulse timing to measure orbit accurately, and if you can measure orbit of X-ray sources again and again and again, in this case, data from many measurements have been put together, some of which are from AstroSat. Rahul is here, I think. So the orbital epochs that you measure, they should line up if the orbital period is fixed, and if you subtract a linear term from that, you would get this residual, and this is a measure of binary orbit of an X-ray binary evolving, and you measuring it within your lifetime. We have found, for example, flares during eclipse of an X-ray binary. And in some cases of cyclotron line, this is the work done by Oshin, we looked at the cyclotron line at different spin phases of the neutron star. Okay, and this here is a neutron star which has 2 poles, 2 pulse peaks. In one of the pulse peaks, we detect the cyclotron line very clearly. In another pulse peaks, we barely detect it. Okay, so that tells us there is some sort of asymmetry, some sort of difference between the 2 poles of the neutron star, perhaps indication of something deviant from a bipolar magnetic field in a neutron star. So AstroSat has done a lot. I can only tell you this much. If you ask another scientist what has been done with AstroSat, you will probably get a completely different view. Okay, that tells you a whole range of things which have been done with AstroSat. So that brings me to ExpoSat and POLIX. I have always been interested in X-ray polarization measurement because it's not done very frequently. It's difficult to do. And there is very interesting science case. So POLIX is this instrument with its electronics, which was put on this satellite ExpoSat with a couple of other semiconductor detectors, spectroscopic and timing device looking in the same direction. That's made in ISRO. So POLIX on ExpoSat was launched earlier this year on 1st January. The measurement principle here is scattering. I said polarization can be measured with 3 different techniques. We use scattering, and it works in the range of about 8 keV to 30 keV. Incident X-rays are made to scatter from a beryllium scatterer, you need low atomic mass material, otherwise the X-rays will get absorbed. And after scattering, they go into X-ray detectors kept on 4 sides, and this whole instrument is spun around the beam axis. So these are different parts of the POLIX detector, and I'm sure our supporting industries who helped us make the POLIX, all of these instruments. The mechanical components are machined in 2 factories in Bangalore. Electronics was assembled here. So I'm sure all of you would enjoy seeing things made from your factories eventually going into space. The electronics again was designed at RRI, and I congratulate the electronics team. The electronics design was whichever way it was conceived on day 1, okay, no single change was required. Okay, very complex electronics which supplies high voltage to the detector, controls the high voltage, pulses are produced, pulses are amplified, that goes into your pulse processing card, analog card to digital card, then data is collected into a common electronics card. You have a housekeeping system. You have ways of communicating with the satellite for data transfer, for commanding, command interpretation, passing on the command to your payload and so on. So entire electronics design, the way it was designed in the beginning, all of that survived. Okay, there was absolutely no change required in electronics design of POLIX from the first version. Well, that's very happy thing to say, and gives us confidence for any future activity that we might join. So this is how POLIX is. You have the collimator, scatterer under it, 4 detectors on 4 sides, B electronics, and this is the whole assembled thing. POLIX is operational from around January 10th. We powered on the high voltage after launch on January 1st. The POLIX crab pulse profile. So X-ray photons come in, after scattering they go into the detector and we detect the events. So the X-ray pulse profile of crab is reproduced from that. So the basic mechanism and the detector functionalities are all fine. One of the detectors has developed an issue of very slow gas leakage. So that may not survive 5 years. The mission objective lifetime is for 5 years. 3 of the other detectors are absolutely rock steady. They may as well last for 10 years. Like one of the AstroSat lax PC detector is operational even now in the 10th year. So same may happen with 3 of the POLIX detectors. The 4th one, I think after about 3 years or so, we'll have to switch it off. POLIX data, you have to measure polarization by rotating the spacecraft and measuring the azimuthal modulation. We, however, are finding the background also to have a modulation. So currently, a lot of additional observation of the background and modeling of it, and trying to find what are the sources for this modulation in the background. That is ongoing. So it's a very happy occasion for us to be here and show you the first light of POLIX. And here you have, I think, almost all members of POLIX team, perhaps not Manish, and members who had left by the time POLIX was launched. Other than that, I think all members of POLIX and some other people who accompanied us during the launch. This was a photograph taken on the day of launch. I think that's all I had to say. Thank you.
Thank you, Biswajit, for such a nice history of X-ray astronomy and how India has evolved in that. We have a time for a couple of questions.
Very nice talk. So I just wanted to know more about these rocket experiments. You said that you can collect data for few minutes. What was the principle? Like you take the rocket out of atmosphere, then which point you collect the?
About 100, so if it's a soft X-ray, then it has to go high enough, like more than 100 kilometers. If it hard X-rays, you may start collecting data even before that. Typically, the rocket will be spinning. Okay, so you put an instrument with a slat type collimator, and as the rocket spins, if you have a bright source, that will give you a blip in the count rate. Okay, then fitting a triangular shape to the count rate, you get the flux of the source and location of the source and so on.
And what limits the time actually? Like it is just a single.
It's basically the velocity at which you leave the rocket, so it has to come down. And I think the limitation also does not allow you to put a rocket to go very far, then it will be outside your range. I don't know what exactly gives the limit, but typical rocket observations last few hundred seconds, maybe maximum 10 minutes of observation. In fact, one X-ray polarimetry experiment at very low energy, like sub keV, is being built at MIT for several decades. Now they have the most advanced version of it. They are planning to put it on a rocket. They have a funding for that. This will give you about 10 minutes of data. Okay, so somebody is working on an experiment for about 3 decades to get 10 minutes of data. However, since this is in a soft X-ray band, soft X-rays you have more photons. Okay, so if you choose your target carefully, which does not have much absorption in that direction, then you may get sufficient number of photons. So it's good for a couple of sources.
Thanks.
Can I ask?
Sadik has a question.
Can I ask?
Oh yeah, go ahead, please.
Yeah, so with this, with the Polix now, what is how long do you intend to study the sources, and I suppose you can integrate over a long time. And you're not in polar orbit anymore. You're
This is not a polar orbit.
Okay.
No, in case of Polix, it's a little complex because Polix requires spin to observe the source. But you cannot spin the satellite all the time, especially when it is sunlit position. If you keep spinning, then there are issues of thermal management and so on. And also power generation is hampered if you are looking at the source all the time and spinning. So which direction will the solar panel be? So Polix operates in a mode where it makes source observation when the satellite is in Earth's shadow and a few minutes before and after. Okay, so Earth's shadow plus about 5 minutes. Then few more minutes goes maneuvering towards the source and away from the source. Rest of the orbit is used for power generation. Okay, so though Polix is in a good orbit, your actual duty cycle is about 28-29% in that ballpark.
and how much?
So,
what is the period of the
since
orbit?
there is no consumable, satellite is in the perfect orbit, there is a lot of fuel left, detectors are, 3 of the detectors in very good shape, like 8-9 months we have absolutely no evolution in gas gain. Okay, high voltage there is no difficulty. So there is no harm in operating it for very long time. For a given source, your observation duration depends on how bright the source is, what is the actual fraction of polarization in the source, okay, and which you don't know in advance. So for bright sources, you would initially make long observations, try to understand the field, like what is the actual level of polarization in different kinds of sources, and then some sources you may have to revisit and so on. Using data from different epochs together, if it's for example a pulsar, then you have a reference, like the pulse peak could be taken as reference and everything else can be put together. If it's a black hole source, then black hole sources have sometimes they are hard, sometimes they are soft, the shape of the spectrum, sometimes they are bright, sometimes they are faint. So you may want to combine data of identical state together. Even if you make long observation, you want to make data from identical state, you want to analyze that together. Some sources have other variations, like some pulsars have what is called superorbital period. Okay, I will not get into details of that, but data from certain phase of superorbital period you want to analyze together. So even if you make long observation, you may then break it into smaller chunks and add those chunks suitably, whatever meets your scientific criteria.
What is the weight of the payload here?
The Polix payload total weight is very close to 130 kg, including the electronics, harness and everything. And the whole satellite weighs, I think, about 450 kg. 130, right? It is close to 130.
Okay, any more questions or? Okay, if not, then we can move ahead with the program. Let's thank Professor Biswajit. Okay, I think so. Next part of the program is, I think, this is the wonderful and ideal occasion to recognize the contribution of various members of the Polix team, not only from RRI but also from the industry partners, as Biswajit has mentioned in his talk. So I would request Professor Biswajit to announce the name of the members to be recognized, and Professor Tarun Saurdeep to hand over the plaque for each member.
As we mentioned repeatedly today, and project of this magnitude and this complexity, doing this from an organization like RRI, where the enthusiasm is there, but we don't have all the infrastructure, okay, to make things. Infrastructure that is there in terms of human resource to work on this that we have, or during the project we could even hire additional people to come and work on it. But the infrastructure is not there, except for making small mechanical things and so on. So the support that we got from our industry partners, both for mechanical fabrication and for electronics fabrication, and more than the making of the things themselves, okay, the flexibility that we received from you in terms of whenever some changes were required, how adaptable you were to the changes, okay, that's what is to be appreciated. So we would like to call upon our all the industry supports, major industry support that we got for Polix. From Centum Electronics, all the electronics that is flown on Polix and the harness that is interconnecting wire between the packages was, conceptualized at RRI, designed at RRI. All the cards were, layout was made at Centum, fabrication was done at Centum. We then tested it, and there are lots of back and forth, and after that final assembly was done in Centum and handed over to ISRO for final assembly with the satellite. So from Centum Electronics representatives, please. Our detector assembly, the initial versions and eventually after many changes, the final version of the detector housing also was made. Detector housing, top plate, wireframes, all of these were made at 3D Concept tools. Mr. Pandian from 3D Concept is here, and we very sincerely appreciate the precision with which the wireframe, detector housing, top plate, etc. were made, and that's why they are still working in space for over months. So 8 detectors were made at
Thank you for the opportunity, sir.
We look forward to. Mr. Srinivas, with whom we have another connection I will not mention here. Aeromech Technologies joined our activities slightly later than 3D Concept, or some very complex machining of the collimator. Collimator has 757 holes made very precisely tapered holes, and all the electronics packages, the mechanical fabrication was done at Aeromech.
We had a lot of trials done.
The base plate and so on, and in this we had enormous number of trials back and forth and so on, and we appreciate your patience with us. Thank you.
Very nice.
Polix design aspect, the person who has been involved with me in Polix from very, very beginning is Rishin, PV Rishin. All RRA members know Rishin, so nothing needs to be mentioned. If you want something to last long, you must have it seen by Rishin. Okay. So Rishin was the main designer for not only electronics, even the detector housing and so on. And he's the main engineer behind Polix. Gopal Krishna is engineer who worked on all of Polix electronics testing and so on, but one key role that must be mentioned is all the onboard software with which Polix is operating, okay, is written and subsequently tested by GK. So he's the software architecture of Polix team. Krishnamurthy is our man for all occasions. He provided the entire ground checkout system for Polix and worked on testing and Polix at various levels, even at individual calls and at package level also. And he's the person with the most resourceful person for the Polix team. Polix detector systems, and as you may have noticed earlier, the lax PC kind of detectors, the large area proportional counter detectors of this kind have large number of wires inside, very thin wires, which have to be placed properly and to last very, very long time and survive the space launch condition. So towards that, and making various versions of Polix, two members, Mamta and Sanda, worked with us for more than a decade. And in the last stages of Polix, all the anode wires had to go through a very complex process. So thank you very much for your patience with that, and we are fortunate that it's working nicely. So Mamta and Sanda for this. Sanda had worked on our earlier versions of other detector systems as well. Yeah. Thank you. Thank you. That's it. So one thing I would like to say is that we are 7-8 members we have seen so far, but 7-8 members don't make a payload. Okay, there is a large contribution of many other members, some of whom are here today, some of whom are not. Some have left, had made major contribution to Polix earlier. I'm fortunate to see Durai. Durai was the first person who made the designs of Polix detectors, collimator, and so on. And Bikram, you please, Bikram will tell us the names of members who contributed to Polix in many different ways.
Bikram, before you move on to naming all of them, Raman Research Institute would like to recognize the contribution from you. So, as the co-PI. Congratulations.
Take a pic. Without mic.
Okay, and last but not the least, Prof. Biswajit Paul, and so Raman Research Institute is happy to recognize this great achievement. Congratulations, heartiest congratulations. With this, back to you, Vikram.
Thank you, I think, for recognizing the contributions from all the members. But as Biswajit mentioned, that these are not only 7-8 people who are part of the Polix team. It's a much bigger team than people have contributed to this project, success of the Polix. So I would just take this opportunity to mention their names, and if they happen to be in the audience, I would just request them to stand up briefly and identify themselves. So I would like to start with the names who has significantly contributed towards the development of electronics. As Biswajit has mentioned, that it's quite complex and it requires really focus and patience. So Mohammad Irshad and Pooja Verma, I think they are not here, but we should recognize them. I think I can just finish the list and then we can upload all of them. It's fine because it's a long list. So these two persons have contributed significantly towards the electronics development. Then coming towards the mechanical development, the significant contributions has come from Hari Krishna Sahu, Ibrahim, if he's around, he can just, yeah, Ibrahim from the mechanical. Then Durai, can stand up, okay, recognize. And Abhilash Kulkarni, I think he is not present at this point. But these are like very skilled people. They have really provided very precise mechanical structure for the Polix that is working in the space. And apart from the engineers, of course, students are the workforce for any search project. Towards the development of the software for the Polix, the students has contributed. So for the software development and the instrument performance monitoring, I would like to thank Ketan Rikame. He's a PhD student. The software, I mean the Polix is producing a lot of data considering a new project, and all of the data has to be efficiently analyzed. The software for which all the modules were single-handedly made by Nandini Srianand. This is there. In addition to this software, the detectors has to undergo a lot of testing, calibration, and of course the assembly. Towards that, there are two particular students, the Hemant Manikantan and Manish Kumar has contributed significantly towards that. This is Manish, and I think Hemant is currently doing his postdoc at Europe, so he's not here. But in addition to these two peoples, there are a lot of other students who has contributed towards the data analysis, support for qualification test. This is particularly the place where students are very useful because this qualification test were running 24/7 at ISRO, and we have to work in shifts. So without this support, it would have not been possible. So I would like to thank Kinjal Roy. He's there. Kinjal. Ashwin Devraj. Okay. Anirban Datta, he is not around. Ajit Bala is there. So these are all our PhD students, and there is a postdoc, Rahul Sarma, who has also contributed. He is currently doing a postdoc with us. Apart from this, for smoother running of any lab, the technical support is extremely important. And two of our persons, Rajgopal and Puttaswamy, has provided excellent technical support. This is Puttaswamy. In addition to this, Srivani KS from EG has provided her expertise in reviewing the software, and then all the simulations that requires GANT4 knowledge was done by a postdoc at TIFR Mumbai, Sujay Mate. He is not around. And there is one more person from TIFR, Dheeraj Dedia, Mr. Dheeraj Dedia. He has provided his expertise to us for designing the power card for the Polix. And Meena G from URSC ISRO has provided her expertise for the design of one of the telemetry card. I think this is what I have currently, but I'm sure there might be some of the names I might have missed. It's not deliberately, but with this, I would again like to congratulate all of the members and thanks for their tireless effort for making Polix a success. So we can give one last round of applause to all of them together.
So I think that brings today's event to an end. Yeah, we can take a photograph with all the team members. And thanks to Tarun for initiating this series, and it's indeed nice, as you said, to have the first talk on the occasion of this polling. Yeah, timing match. So. We missed that. Wasn't that a? Oh, okay, that is nice. that was nice.
Was Shri Jitendra Singh, Union Science and Technology Minister. His first comment was, हमने तो आपसे ज़्यादा tweet किया है इसके बारे में, Polix के बारे में. So Jan 1st they had tweeted. RRI did a bit, but I think not at the level which Science and Technology Minister felt was. What he had done was much more, is what he said. But glad that there was so much attention, and we got a prime spot in terms of January 1st, first launch from the country. And I think that's really
2nd January we had powered on the instruments.
Yeah.
Yes. So we were all in ISRO.
Yeah. Okay. So thank you everyone for coming.
So the Polix team members can
please
present and past if you gather here.
Whoever,
just take a photograph.
Let's take a full picture.
We do miss people who contributed a lot in the past and not.
Also
not in
our
the team
industry
now.
partners, please. The whole.
Yep.
Nowadays they fit huge collaborations into pictures. I don't know how, but so this is easy to do probably. So you have to stand up somewhere there. Please bunch up a bit. Hey, good. Hey, so first conference talk, huh? Yes. Very impressive. अरे साइड में क्या, बीच में खड़े हो जाओ, बैठ जाओ. Young guys. Pull up the chairs and stand. Go there. Yeah. At the no. On the footsteps of the masters.